Well, I had a good 20 years.
Yeah, that's the one bad thing. I'm washing my hands. Every time I reach it,
Yeah, I was going to say that.
and as soon as we walked in, I listed it. This one doesn't need its own board. She's like,
Okay, new schedule has been passed out on D2L. If you lose this, it's on syllabus and course information. It's course schedule after snow day. It really wasn't a snow day, but that's where it's at. I'll pass your exams out towards the end of class. Yeah, let's see. The average was a 74. I think the median of 82, like I said, is a better average though. So.
Okay. That one was what?
All right then. Hello? Hi. Y'all ready? We're starting chapter 10, which is primarily dealing with series, but there is a little bit of sequences in there as well. So 10.1 is an overview of both sequences and series. 10.2 we look at sequences, series for the rest of the way. And virtually the goal of chapter 10 and chapter 11 is to take something like e to the, sorry, the smartboard's really weird, so bear with me. Something like the integral from a to b of e to the x squared, and convert that into an integral from a to b. For now, we'll just say an infinite polynomial. And that's kind of the heart of these next two chapters. It's one of the key aspects of calculus outside of integration and differentiation, that functions like e to the x squared or functions in general can be represented as infinite polynomials. I'll show you a few images of kind of how that works, but like when you plug into your calculator like e to the 0.5, it's calculating e to the 1/2 in this infinite polynomial as opposed to e to the 1/2. So it's using like x's, x squared, x cubed, x to the 4th, and combinations thereof to give actual values for sine, cosine, logarithms, exponentials, and I believe a lot of computers use a portion of that as well to compute values. So here, the idea is, it might be helpful. If not, we go over this. But the idea of the linear approximation. Does anyone remember that? So we can use the tangent line to approximate function values. So what we're looking at is the function e to the x, and we say find the equation of the tangent line at the point 0, 1. And so we come up with the equation of this tangent line here. And as long as we're really close to the x value of 0, then we see that's a pretty decent approximation of e to the x, right? You have to say really close. Instead of using the curve, I'm going to use the line because a linear function is really simple, right? Well, the idea of those infinite polynomials or power series is to improve upon the linear approximation. So if we looked at the linear approximation as opposed to the quadratic approximation, and then try to fixate on the point at 0, 1 and see how much of the colored graph overlays the black graph of e to the x. So we get better and better approximations the higher order polynomial we use. So there's a quadratic approximation, and then a cubic approximation, 4th degree, a 5th degree, and so on and so on. I don't think I can zoom out, but that color's hideous. But there's like a 47th degree approximation of e to the x, and we can see that blue curve is an actual polynomial. We don't know what it is yet, but that's kind of the idea of series, is to be able to express a function as a polynomial, specifically an infinite polynomial. And finite polynomials, in some sense, if we're around the place, like we constructed this polynomial here at the point 0, 1. So as long as we're close to 0, 1, this polynomial is a good approximation for all of these other x values.
Is this what leads to like the Taylor series?
Yeah, exactly, yep. Yep, so this is a Taylor polynomial. So we see the same thing for cosine here. There's the tangent line at 0. There's your quadratic approximation. And cosine's an even function, so we wouldn't have a cubic approximation of cosine. But then we have a 4th degree. See, the cubic is the same thing as the quadratic. And we have a 4th degree approximation, a 50th. So that's a x to the 50th and some other terms. But we see that it matches up with cosine perfectly. So instead of using cosine, maybe we wouldn't get carried away and go out to the 50th term if we wanted to approximate. But certainly using like an 8th degree polynomial is much better at approximating all the other values around 0 as opposed to the linear approximation, which is pretty terrible here. So it takes a long way to get there. There's a lot of sort of weeds we have to hack our way through in order to get to that stuff in chapter 11. But just kind of keep that in the back of your mind. This is sort of, all of this stuff is sort of is culminating to that. That's, well. So chapter 11, we're looking at, like I said, infinite polynomials. And Taylor's theorem. So again, think of these things as like the linear approximation, only better. Before we look at those, we look at series. Before we look at series, we look at sequences. What's the difference? Sequence, we'll see here, a sequence is just a list of numbers. Series is when we start adding those numbers together. So, for example, 0, 1, 4, 9, 16, etc. That's a sequence. A series would be 0 plus 1 plus 4 plus 9 plus 16.
Is that just summation?
Yeah, and these are written as infinite sums. I mean, they can be infinite. I guess we can make that a little more specific. well, whatever. But that's the difference between the two. We don't do a whole lot with sequences. They do show up in the overview and in 8.2. Then pretty much after that, we're all focused on series. Because ultimately, we're going to be looking at infinite polynomials that represent normal functions like e, sine, cosine. Yeah.
There's a series. Is there also a parallel? A section for like parallel?
What do you mean?
Because, well, I'm thinking because mathematically, there's like when you deal with circuits, there's a circuit that's done in series and parallel. I wonder if there's like a correlation. Sorry.
Not that I would have to be more familiar with that, with the jargon and circuitry to answer that fully. But I don't think so. I don't know. Okay, so that's our overview. Most of it is series. The first two sections we get a little bit of sequences. Also, since we had to miss that class, some of this stuff, some of the examples I do have in our notes, we might have to skip just for time purposes. So a sequence, like we said, is just an ordered list. So I'll just write our example down again, just as one specific example. A generic form here. Yeah, sorry.
No, go ahead.
Do you have a question?
I would say, just look like a pattern.
Yeah. So the patterns we're going to look at are recursive formula and there's explicit formulas. But the general way to look at this is we've got a sub 1 first term, a sub 2, a sub 3, a sub n, a sub n plus 1, so forth. So that the subscript here is referred to as the index. And we always index by the counting numbers. So the index always just move their discrete counting numbers, 1, 2, 3, 4, 5. Sometimes they can start at 0, 1, 2, 3, 4, 5, etc. But each term is generated by the next index. When we increment the index 1, it gives us another term. So, like this would be the nth term. This is the third term, etc. Okay, so lists of numbers, there's two ways that we look at representing those. Recursive formula, and recursive just means that the next term is based on a previous term or terms. For example, if we define a sub n to be 2 times a sub n minus 1, where a sub 1 is equal to 3. So here the next term, the nth term, is defined as 2 times the previous term. And so we have our first term, we can build all of the other terms from that. So our first term is 3. What would the second term be? Yeah, it's 2 times the previous. So the second term, just imagine this is 2. A sub 2 is 2 times a sub 2 minus 1, a sub 1. right? So, I mean, some of these, once you see the patterns, don't really need to think about it much. Okay, so that's recursive. Well, next terms or terms depend on previous term or terms. Explicit. Hopefully that term's kind of obvious at this point. Explicit functions, we've been looking at y equals to x. So it just shows you explicitly how we get the next term. So let's say, for example, a sub n was 2 times n. And we'll specify that n is 1, 2, 3, etc. So what would the list of numbers be for this? Yeah. 2, 4, 6. So that's an explicitly defined sequence. Do you have any questions on terminology there?
So is this supposed to like graph, like you put points on a graph? Like that's how it's coming to?
Yeah. It's well, these. If we looked at the graph of these, it would just be a discrete set of points. It's not continuous. So. So like here's 2x plotted with from 1 to is that 10? So we know the line y equals to 2x is a continuous line. Here we're just getting those discrete points when the index is 1. So a sub 1 is 2, then a sub 2 is 4, 6, 8, 10, 12. So it's a discrete set. We're not going to use sequences to like graph functions or anything, but they can be thought of as the discrete analog to functions for those positive x values, anyways. So, are there any other questions on how we're coming up with any of this? Does that make sense? And the two are interchangeable. For instance, like I could take the recursive formula, the sequence generated from the recursive formula, and come up with an explicit formula for that. Similarly, with the explicit formula, I could come up with a recursive formula. So it really just depends on the instructions and what they want you to write out. No, I did the line to him. No way.
I was gonna say, that's the most level line I've seen as well. So.
Just say yes.
Okay, so explicit formula for this one, we could say, for instance, a sub n equals to 3 times 2 to the power of n minus 1. So let's check, where would n have to start then? Yeah, so n equal 1, 2, 3, etc. So when n is equal to 1, let's just check this. Does a sub 1 equal to 3? So we have 3 times 2 to the 1 minus 1 equals to 3. Sorry, I gotta scoot this down though. It's crummy down here, so we'll go back up if we need to. A sub 2, and it's 3 times 2 to the 2 minus 1, which is 6. And we can check the others if we wanted to. But we can represent this explicitly. Yeah. This one here, where we defined it explicitly, a sub n equals to 2 times n. I guess that's blue now. Recursively, how could we define that 2, 4, 6, 8? We have to say this term is a previous term.
A sub n equals a sub n minus 1 plus 2.
So the next term is the previous term plus 2. What do y'all think? Does that work?
Given that a of 1 is, or 2, sorry.
Okay, good. Yeah, you want to specify a sub 1 is equal to 2. Otherwise, you can't continue with the recursive formula. Is anybody familiar with the Fibonacci series? Yeah. So that's defined recursively, but you need 2 previous terms. So it's the next term is the previous term and the previous one to that. So you basically need 2 initial conditions because you've got 2 previous terms here, 1 previous term. We need that starting condition. Yeah.
Is the first term always going to be like the first term, not like the 0th?
Yeah, we consider it the first. Even if it's like a sub 0, it's still the first.
Okay.
Yeah. And I suppose that's, I suppose that could differ from text to text. Just semantics. And then once you have a recursive one, we could also define it as the next term is the previous term plus 2. So it's just the same way to write what we've already written. So those things aren't unique. Multiple ways to represent a series. Or sorry, a sequence. So the sequence 1, 4, 9, 16, et cetera, write out the next 2 terms. So the next 2 terms would be what? 25, 36. Okay, 25 and 36. What's the explicit formula for that sequence? Yeah. So whatever term, wherever we're at, that term is defined as just the index squared. N equal 1, 2, 4. How about a recursive formula for that sequence? We have to say something, to the effect of, the next term is something to do with the previous one, or we could say the next term is something to do with the previous one, etc. Maybe we start off with this one, a sub n.
Say a sub n equals the square root of a sub n minus 1 plus 1 squared. Nothing.
Nope. Yeah? Okay, then what's next?
Plus 1 and then squared. The whole thing.
Okay. So the next term is the square root of the previous term plus 1 squared. Let's see if that works. Let's just check it here. So a sub 1 is equal to what? We have to define that, right? Because we can't, if we would say a sub 1, then we have to put in 0 here. Okay, so a sub 1 is equal to 1. So the second term, a sub 2, should be the square root of the previous term plus 1, and then we square all of that. So we have 2 squared, which gives us 4. Okay, so that's promising.
Better be.
The third term, we take the square root of the previous. So let's just write it out. Square root of a sub 2 plus 1 squared. That's the square root of 4 plus 1, quantity squared, which gives us 9. So 4. Okay, seems to work. Again, we could also kind of represent that. We could say that a sub n plus 1 is the square root of a sub n minus 1 plus 1 squared.
Not A of n, just A of n.
Oh, a of n, yeah. All right, any questions on that?
How do you come up with these various quantity?
You find a pattern.
Some of it's trial and error. Like you've gotta just mess around with it. I mean, you know, that's not obvious. There's also other ones that'll work too. So they're not unique. Just go for the most obvious. If that doesn't work, then try to revamp. Sometimes you can look at, like what I have to add to get to the next term. Like the difference between the two, stuff like that.
Something I end up doing a lot is trying to get whatever way I can, if it's like an exponential function or it keeps going in one way, trying to get to the index and then turn the index back into the number.
Yeah, and really that's the key, because especially when you're writing it out, I think it's really a toss-up as to which one's more difficult. Here, the explicit formula was like really easy. We saw that they were just squares. When you're using the or writing out the recursive formula in particular, it is very helpful to think about, matching these numbers up with the index. So 1 to 1, a sub 2 is 4, so 2 and 4. A sub 3 is 9, 3 and 9. Like try to figure out some sort of pattern with those. Helpful with explicit formulas, and sometimes recursive too. But there's really no surefire way to. There's not an algorithm to say, you got to do this process and you'll get it. Okay. Any other questions? Find the first 5 terms in the sequence given as follows. Does everyone know what the factorial sign is? Yeah, the exclamation mark here.
We work out too.
Yeah, I mean, you might see it in algebra. It's very common in statistics, but this is read as in factorial. So first of all, 0 factorial is defined as 1. We'll just look at a few of these to get the idea. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So n factorial is n times n minus 1 times n minus 2 times all the way till we get to 1. So our first term, a sub 1, index is 1. You've got 2 to the n over n factorial. So I'll just write this here so we can match. So a sub 1, 2 to the first over 1 factorial. That's just 2 over 1. First term, second term, a sub 2. A sub 2 is 2 squared over 2 factorial. So what would that give us? Yeah, 4 over 2 factorial is 2 times 1. Oops. 2. Third term. Eight over 6, yeah, it's 2 cubed over 3 factorial. Or we can say that's 4 over 3. Fourth term. Hmm. 16 over 24. Do y'all agree? 16 over 24? 2 to the fourth over 4 factorial. Okay. And fifth term?
2 over 120.
What was the top?
32.
32 over 120, yeah? It's the first 5 terms. We have 2 to, whatever, 8 over 6 if you like. 16 over 24. 32 over 120. But those are our first 5 terms. Easy enough? Okay. Yeah, sorry about that. How about the first 5 terms of cosine n pi? Here, what's the first term? Yeah, it's the cosine, let's write it out. It's the cosine of 1 pi, which is -1. The second term, that's now the cosine of 2 pi. The third, -1. Fourth, 1. And the fifth, -1.
So would it not exist since it's not really approaching a number?
No, we're not going to think of, right now we're not thinking of sequences, limits of sequences. We're not thinking about that right now. But if you are thinking about it, then right, it doesn't have a limit. We will start thinking about limits of sequences though. First 5 terms for the sequence, -1 to the n times n. What's the first term there? -1 to the 1 times 1. -1. The second term? negative 1 squared times 2, 2. Third term, negative 1 cubed times 3, which is negative 3. The fourth term, 4. The fifth term, negative 5, right? So there's two examples of different ways to alternate a sign, right? The alternating sign coming from like a periodic function like sine or cosine, or we could just have this negative 1 to this power here. So either one of those act as an alternation between positive and negative.
Is that a cosine or sine cosine? Since it's
No. Yeah, I don't know. We can't really attribute sequences to any function, not in a continuous sense, because they're just those discrete packets of points, right? They're not these continuous things. Okay, do y'all have any questions on any of that? Okay, the limit of sequences, this is equivalent to the limits that we've computed throughout Calc 1 and even in Calc 2. I don't know if you can see that. It says if the terms of a sequence approach a unique number as the index increase, we say that there's the limit as n approaches infinity on that sequence equals to L, and the sequence converges to L. If they don't approach a number, then we say it diverges. So virtually equivalent to limits that we've computed before. So let's write out the terms, first 5 terms of the sequence 1 over n plus 1. And if the sequence appears to converge, make a conjecture about the limit. If it looks like it diverges, just explain why. So the first term would be what? This one's defined explicitly. Yeah, 1 over index plus 1, 1 over 1 plus 1. Let's try to fit it here. The second term is 1 over 2 plus 1. Third term, 1/4. Fourth term, and fifth term. Okay. So I mean, we can write these terms out just so we can see them. 1/2, 1/3, 1/4, 1/5, 1/6. Okay, so there's our sequence. Does that appear to converge or diverge? Okay, so our guess is that it converges. What does it appear to converge to?
0.
Yeah, so the way we can look at that is just through a limit. So what's the limit as n approaches infinity on 1 over n plus 1? 0. Yeah, they get smaller and smaller.
So is that the same with anything? N is always on the bottom. The approaching infinity is always going to go further.
Yeah, well, it depends on, kind of. It depends on
The
the...
constants on top, I guess.
Yeah.
Okay.
Exactly right. So converges to 0 is something we can conclude. Okay, how about the sequence -1 to the n plus 1? would the first term be? 1. Second term?
Negative.
-1. The third? Fourth? Fifth? All right. Get the idea. So our sequence: 1, -1, 1, -1, 1. Converge or diverge? Diverges. So it diverges, just oscillating in between 1 and -1. It's not approaching a single finite value. So just make sure it's kind of confusing at first when we start looking at series as well, relating the limits of a sequence to a limit of the series. It's really easy to get those things jumbled together. They're two completely different things, so you got to keep those totally separate. I mean, some of the things translate somewhat, but when you start mixing sequences with series, those ideas, it's just bad news. Okay, write the first 5 terms of this sequence. It's defined recursively, and state whether it appears to converge or diverge. So I'll give y'all a minute or two to write these out. So what's a sub 2? -3. A sub 3? +9. A sub 4? -27. And a sub 5? +81. So that's just the first 5. Continue on. There's our sequence. Converge or diverge? Diverges. Again, the terms are growing without bound in magnitude. So grow without bound in magnitude or in absolute value, however you want to say that. Questions on that? Yeah.
I guess, what do you mean by that? They grow without bound and magnitude?
In absolute
Like any exponential could follow that.
in absolute value.
Yeah, but if it was just growing in magnitude, wouldn't that mean it was just going up towards infinity? Or do you mean anything that just, like, I feel like there should be a better explanation than that.
Well, what explanation do you like?
I don't know, just like, it doesn't seem to.
So usually when we think of magnitude, we just think of the number. We don't think of the sign associated to the number.
Well, like,
If you think of
exponential,
magnitude as
like,
something
what-
different.
Like the negative numbers are getting more negative and positive are getting more positive.
Yeah, so like
Oscillating.
they do oscillate. It's 1, and then it's -3, and then it's +9, and then it's -27.
It's not converging to a set value, so.
Yeah, it's like the delta
Right.
between them grows, so I could say it doesn't even like that. It's like if I drew it just without it, just saying 3VA, that would fit the same, but it should converge technically to infinity. Or like this.
Well, you gotta be careful, we don't say anything doesn't converge to infinity, we would say that.
It approaches it.
Yeah, so if you wanna say that, if you wanna say that the terms in the negative and the positive direction get approach infinity and negative infinity, that's fine, you're saying the same thing. You're saying dog, I'm saying canine.
No, they converge, it's just like, look at me, like.
Okay, example 8, how, before we write the terms out, let's just looking at the way that things defined explicitly, what would we think about the sequence there? It's going to converge on 3. Do y'all think that's a realistic? Okay, let's see. And sometimes the first 5, first 10 terms might not be enough to just look at as a data set to say, oh yeah, this is going to converge. Like, we need more robust measures for that, but we'll get into those.
Since the power are the same.
Yeah.
Function analysis.
Yeah. Rational function, limit at infinity. Yeah. What's the first term? 3/2. The n is 1. 3 times 1 cubed. 1 cubed plus 1. Second term. 24 over 8 plus 2. Third term. Yeah, I'm not sure. 2381 over
30.
Okay. Fourth term.
Over 68. That's we got 192.
192.
Okay, whoops. Not just calculator. Use the calculator.
Oh, you
And fifth term. 375 over 130.
Yeah.
So now if we're kind of looking at those, wondering if it converges or diverges, it probably makes more sense to look at them in a decimal, as a decimal. Okay, so that's 1.5. This is 2.4. What's 81 over 30?
2.7.
2.7. 192 over 68.
2.82.
2.82. And 375 over 130.
2.88.
2.88.
Trace.
All right, we'll write those out.
That's approaches infinity.
1.5, 2.4, 2.7, 2. So I mean, maybe that's not enough. You see the fourth and the fifth, like it didn't jump all that much. 0.82 to 0.88. Maybe you think it converges to like 2.85 or 2.89 or something. But
So
like
it
we
does
said,
go to infinity?
well, so the way we can check convergence is we can look at the limit at infinity.
just click.
So as that index gets larger and larger and larger, what is that very far tail term? get closer and closer to.
So what if you just use like rational?
Yeah. So I mean that's our justification. Just a normal limit at infinity will do. Is that what you were referring to? How to compute the limit?
Yeah, so if you hold up that 1/3, you'd be big, at the end you get 3 times n squared over 1.
Well, yeah. We're looking at this as equivalent to just 3n cubed over n cubed for large n, which is equivalent to 3. Maybe it's a good place to remind that when we compute limits at infinity on those types of functions, quotients, the general approach is to divide by the highest power in the denominator. So as n goes to infinity, it's 3n cubed over n cubed plus n. And we're really dividing everything by n cubed.
That's only if it's a rational function.
It works for, the same logic applies to like exponentials as well. So here we've got 1 over n squared, but the limit that n is approaching infinity. So this term here just goes to 0, which gives us 3 over 1 or 3. With rational functions, it's easiest to look at the leading term over the leading term and simplify. But that's kind of what you're doing when you do that anyways. And as you can imagine, like with some of these, L'Hopital's rule could show up, right? So just normal limits. So we would say that converges to 3 just from the limit itself. If you're unsure, then maybe compute 5 more terms and see what those look like. We're going to skip the Fibonacci.
I was excited about that one.
Oh, sorry, I'm letting you down. Infinite series. So now we just take the terms of a sequence and add those all together, is what a series is, infinite sum. So let's consider the sum from, our index will be k equals 1 to n of 1 over 2 to the power of k. No, it's not quite. So the integral was what kind of sum?
Riemann circle.
A Riemann sum, which was a infinite sum. So this is a finite sum. We do look at infinite sums, though. Yeah, Izzy?
Does it always have to be like addition? Or be like subtraction or multiplication between the terms?
Sure, yeah. Yeah, so...
Will that like be inside the...
Yeah, it would be attached to this thing right here. Like if that were like negative a to the k, it'd be 1 minus 2 plus, whatever. So there could definitely be subtraction in there. And we do end up, I think it's 10(7) where we do look at alternating series. But yeah, certainly could be negative in there. All right, what are the first few terms of this series here? Yeah, so the first one is 1 over 2, so we have 1/2 plus a 4th, so forth, plus an 1/8. It's really the same question here. If I add up all of those terms, right now it's just finite, but if I went out to infinity, would that actually converge to a single value? And those are the questions we associate with infinite series as well. Does it converge or does it diverge? And then in chapter 11, we replace or we throw a variable into the, so maybe we have maybe we have x over 2 to the k, and then we see, can we represent that as a function? Does it converge? Is saying if this series converges to a function, that means that function can be represented as that series. So in that context, convergence and equality are really the same thing. Okay, so where do I want to go with this? Question, I guess first question. Does the series converge? So we've got to remember this is not, it's no longer a list of numbers. It's not 1/2, 1/4, 1/8. It's all of those things added together. So as we'll make it a little bit more official, but what we have to do here is look at partial sums. So we're going to look at sequence of partial sums. Again, sequence back to a list of numbers. So let me see, 1, 2, 3. Maybe we'll go out to 5. Okay. So partial sums are just the sum of the first, whatever. The third partial sum is the sum of the first 3 terms. The 10th partial sum, I would add the first 10 terms. So the first partial sum is just the first term, which is 1/2. The second partial sum is now 1/2 plus 1/4. The third partial sum is 1/2 plus 1/4. No, that's plus 1/8. Does that make sense? Okay, we'll look at maybe up to the fifth partial sum. The fourth, 1/2 plus 1/4 plus 1/8 plus 1/16. And the fifth. Just to see, like, we'll continue, we could continue in this manner to look at the 100th partial sum if we wanted to. All right, so we have 1/2, a 3/4 rather, and we have 7/8, fourth partial sum, 15/16, and the fifth partial sum, 31/32. So it's basically we're just step by step adding up each term, and then here we're stopping at 5 and saying, does that seem like that particular sum, 31/32, as a result of summing the first 5 things? Does that seem like that will converge to something? So let's write out the actual sequence of partial sums. 1/2, 3/4, 7/8, 15/16, 31/32. The idea of partial sums is really important. We will talk about it more, but basically when we start summing series, it's one of the only instances that we can actually determine what the series sums to. So like in a lot of these that we'll see, you'll be able to determine that it does converge. Like, hey, this series converges, but oftentimes there's no way to determine what it converges to. So we'll say for now, if you can find a formula for the nth partial sum, then you can determine what the series will converge to. And that's kind of where we're going with this. So now that we've got a sequence of partial sums, can we find a formula for this? Sequence. So just, it's worth pointing out, this was S sub 1, this was S sub 2. So we want to try to match our indices with the actual term that we're getting. The denominators should be pretty easy, right? The denominator is always what?
Two.
Yeah. So when n is 1, this is 2 to the 2 to the first, 2 to the second, right? 2 to the third, 2 to the fourth, 2 to the fifth. So there's no reason for us to expect that would deviate. Like the 100th term, the denominator would be 2 to the 100th power.
Would the numerator be 1 plus 2 times n minus 1?
So thinking 1 plus
2 times the quantity n minus 1.
2 times the quantity n minus 1. Yeah, what do y'all think? Does that work?
Couldn't we also just do the whole thing as 1 minus, and then what we just said we got as the denominator? So 1 minus, and then 1 over 2 to the n.
That over 2 to the n?
No, just the 2 over the n, 2 to the n, just 1 over 2 to the n.
Just 1
1
over.
over that, and then 1 minus that quantity.
1 minus.
One.
1 minus 1 over 2 to the n.
Yeah, that works.
Yeah. But not this one. Okay. All right. So 1 minus the quantity 1 over 2 to the n. Does that work? For the numerator? It's 2,
That's for the whole thing.
1, 4, 3. It's for the whole thing?
Yeah.
Okay. Well, that would.
Mine is still.
Couldn't you do 2 to the n minus 1 over 2 to the n?
Yeah, that's the same thing. This is equal to this right here. So either one of those work. Yeah? Now, thinking about it in terms of how do I want to represent it? If I have multiple ways to represent it, maybe it's straightforward and multiple representations, but if we're thinking about the series 1/2 plus a fourth plus an eighth, and then we're looking at the partial sums, if we're trying to determine whether that converges, what are we going to do with the formula for the nth partial sum?
Calculate its limit.
Take the limit.
Yeah, take the limit as n grows towards infinity, or goes to infinity, right? So that way we're calculating the 1,000th partial sum. What happens when we sum 1,000 of the terms, or the trillionth partial sum if we sum a trillion of those terms, right? So that 2 to the n minus 1 over 2 to the n, or the 1 minus quantity 1 over 2 to the n. Either one of those I think are pretty comparable to compute a limit at infinity. So here's our formula for the nth partial sum. We all agreed with that? Okay. So let's go ahead and make that connection. The reason that's important is because this formula here, if we go back to the series from 1 to n of 1 over 2 to the k, what we know now is if I sum up the first 50 terms, the first n terms, that sum is going to look like this right here. So let me erase this. The first n terms, I can represent my series as 2 to the n minus 1 over 2 to the n. So instead of messing with the representation of the series as it is, if I go out to n terms, that's what the sum will look like, regardless of where I'm at.
This is the bar trick that you can do where you can, I don't know, do a summation or something. Does it sound familiar?
No.
I thought it was one where you can tell somebody to try and count it. They can do it individually out, or you can just use that trick.
Oh, I don't know. I know there's lots of jokes like referring to things like this where it's like, the guy asks for a beer and then half a beer and then.
It's like you should know your limits.
Yeah, that one and the another derivation. The bartender's like, "You trying to put me out of business?" Yeah, there's a bunch of them, but I don't know the actual bar trick. So, what we're saying is, if I want to compute the sum from k equals 1 to infinity of 1 over 2 to the k, then that's equivalent to looking at the limit as n goes to infinity on 2 to the n minus 1 over 2 to the n. Right? And let me erase that, make it more consistent. Okay, so now I have the infinite sum. Here's what it's equal to. Does it converge? What's the limit? The limit as n goes to infinity of this is what? It's 1, yeah. So if I add 1/2 plus a 4th plus an 8th, ad infinitum, that will converge to 1. But here, this thing is worth remembering in general. If I'm asking a question about whether or not an infinite sum converges or not, it's equivalent to the process we just did. Can we find a formula for the nth partial sum? Because this sum right here from k to equals 1 to n of the series is the same thing as the infinite, or as the nth partial sum. So formula for the nth partial sum, if we can compute that limit, and it equals L, then we know that the infinite series converges to that limit as well. We'll make that more precise, but it's worth pointing this out since we're already talking about it. Yes, you can use the squeeze theorem here with some of these too. So I meant to put a better picture there, but let's see if I can find it. It's kind of a visual representation of what's what's going on, why that converges to 1. Okay, so we start off with the convergence here, the area is 1. I'll just move this. There's our next partial sum, the 4/2, or 3/4 rather. And so all of these are our subsequent partial sums. So how far they go out to the 20th partial sum.
It really does just get to the point like, okay, is this good enough for you?
Yeah, well,
Is this enough?
yeah, I guess.
Like, how specific
sort
do
of-
you need to be? How close do you need to get to 1 before you count?
Yeah, that's always the idea. You know, like you're building a part or something, a bridge, a washer. I don't know. There's always a threshold or a tolerance, right? You need to be within 1/1000th of a centimeter for this part to fit where it needs to go, right?
Yeah,
So, you know, with a lot of this stuff, it's not the case where we have to carry them out to infinity. If I want to know what the antiderivative from a to b of e to the x squared is, like I don't have to carry that out to infinity. I can't. It's just a matter of how accurate do I want to be with it. If I want to be super, super accurate, then I'll look at maybe 100 terms. If I don't need to be that accurate, then I'll just look at the first 4 or 5. But, you know, I don't know why this isn't showing up. It's kind of annoying.
Yeah, I was learning that NASA uses 10 digits of pi to do all their orbital mechanics, because that's enough for accuracy.
That's really accurate though.
Yeah.
10 digits.
They said like 50 digits, you can calculate the observable universe to like the degree of error to like a fraction of an atom or something.
Wow.
It's great.
Yeah, there you go. Wow.
Fun facts.
Fun facts. Trying to keep it fun, guys.
I don't know. That's in your textbook. Reference that if you want. Visual aid.
Be a cooler piece.
Yeah, and so when we computed that limit, when we computed this limit and said it's 1, we're just looking at leading term over the leading term. 2 to the n over 2 to the n is 1. You know, equivalently, if we looked at our other representation, 1 over 2 to the n approaches 0, so it's 1 minus 0. Okay, any questions on that? Let's see. All right, let's take a break and then we'll continue 8.1. Sorry, 10.1.
It's like a better form. I was just
Are you ready?
Yes.
There's some paradoxes here too. This is in 10.3, but it's a pretty interesting problem. Sometimes referred to as the Koch snowflake, K-O-C-H. I don't know if it has anything to do with the Koch brothers or not. Probably not. So the idea is to start off with an equilateral triangle, and then you find the midpoint here of each side, and then you use that to come up with another equilateral triangle. So like this. And then you do that indefinitely.
Which is symbology.
What?
How is this the
Because eventually it just becomes circle.
What was the thing where you zoom in and
Fractal?
yeah.
Yeah, it could be considered. I don't think it's a fractal. But the idea is that the paradox here is that it has a finite area, but its perimeter is infinite. So there's an exercise in the textbook that actually kind of where you prove that. If the finite area, infinite perimeter.
It's called, what is it, Koch's?
Yeah, I forget, the textbook doesn't call it that, so if you try to look it up in the textbook as Koch snowflake, it doesn't show up. Maybe it's Koch, I don't know. Let's go with Koch, it's less, it's further away from other word. Y'all keep me young.
Full class.
So here, what we wrote in parentheses here, I just want to reiterate that if we take, in order to find the, in words, in order to compute an infinite sum, as long as we can find a formula for the nth partial sum, we can find the limit of that, which is equivalent to the sum itself. So the infinite sum is equivalent to the limit on the nth partial sum. Okay. We'll see that in a few pages, but that's the idea. So consider the infinite series 0.3 plus 0.03, etc. Let's find the first 5 partial sums. Okay, the first partial sum is always the first term. So the first partial sum is 0.3. The second partial sum is the sum of the first 2 terms. And that's equal to 0.33. Third partial sums, sum of the first 3 terms. And notice we could write the third partial sum as, the first term plus, well, maybe let's not talk about that yet, plus the next 2 terms. So that's, the third partial sum is 0.333. Yeah. So the fourth partial sum, I don't run out of space here. Is 0.3333. And the fifth partial sum, 0.33333. Okay. And then part B says make a conjecture for the value of the infinite series.
1/3.
Yeah. Seems reasonable. I know it doesn't ask for it, but let's just kind of look at that and see what's happening. So we've got our series. So if we wanted to express this as in closed form, as the sum from k equals 1 to infinity, how could we express that?
3 over 10 to the k.
Okay, so 3 over 10 to the k. What do y'all think?
Should you just do 1 over 3?
To the k? No, because then we would get 1/3, 1/9. So we have 3/10, 3/100, 3/1000, right? Yeah, let's write this out. So in order to make a more concrete statement about that, if we look at the infinite series, we say, well, what is the nth partial sum? And look at the limit on the nth partial sum that is the same as the sum of the series. So maybe we can kind of just leave it at that, because that's going to lead us into the next definition for infinite series. Which is kind of what we saw with our 1 over 2 to the k example. Upper bound is infinity, makes it an infinite series. And then the partial sums listed here, the sum of a sub 1 plus a sub 2 plus a sub n, gives us our nth partial sum. And here is where they're making that the nth partial sum is equivalent to the sum from k equals 1 to n of that series. Okay, so that's finite. Then when we look at the infinite series from k equals 1 to infinity of a sub k, whatever that statement is or that expression is, that's equivalent to letting n go to infinity. But this right here, I don't know if it printed out very well for y'all, but since this right here is the nth partial sum, we're going to replace this with its nth partial sum s sub n. So computing the sum is the same thing as computing the limit on the nth partial sum. So that's kind of where that is stated. If it converges, then we know what the sum converges to. If it diverges, then we know the sum diverges. So, the problem with that is a lot of these series that you'll see, it's virtually impossible, highly difficult to come up with a formula like 2 to the n minus 1 over 2 to the n for a lot of terms that we see or series that we see. Just because there isn't a definitive pattern between the numbers that you're looking at. So it's kind of like if and when we can express the nth partial sum as a formula, we know the sum of the series. Okay, so the series 2 times k over k plus 7 root k, we want to find the first 4 terms of the sequence of partial sums, and then make a conjecture about the values of the value of the infinite series. Okay. First partial sum, second, third, fourth, we need those terms. So let's first start off by finding the first 4 terms. We're not adding them yet. We're just finding we're listing the sequence. The first term would be what? 2 over 1/4. 2 times 1 over 1 plus 7 times the square root of 1. It's 2 over 8, which is 1 over 4. Second term,
Over 2 plus 7 root 2.
yeah, so this is where we're going to have to start maybe looking at the decimal values. So 4 over
0.336.
plus 7 root 2. 0.336. Third term. Write it out explicitly. 6 over 3 plus 7 root 3.
0.3, no, 0.4.
That's it?
Yeah, it's 0.3967. so-
Okay, 0.3967. Okay, fourth term.
0.4p.
All right, so now that we have the first 4 terms, then we can look at the first 4 partial sums. So our partial sums, first partial sum is just the first term, so it's just 1/4. Second partial sum is 1/4 plus 0.336. Which is something. Third partial sum, 1/4 plus 0.336 plus 0.3967. Let's just say that's 397. And the fourth partial sum. Is that? Make sense? Partial sums?
Just so you know, everyone, 8-4, a little bit up, you did 4 plus 7 square root of 8.
Oh, 4, yeah, square root of 4. Not bad. Thank you. Okay, so what do we have? Second partial sum is
0.586.
So 0.586 for our second partial sum. The third partial sum, 0.836. Fourth, 1.427.
Yeah.
All right, so just let's write those out. Sequence of partial sums.
Yeah. I got something different for partial sum of 3.
Of 3.
0.9827. Yeah.
0.9827. 0.9827. .983, yeah. So really, we're just looking at the subsequent sums here to see if the series appears to converge or diverge. There's the first four partial sum, sequence of partial sums. Does it look like it's going to converge or diverge? I mean, we go from a quarter to more than a half to almost 1 to almost 1.5. So just based on those limited four, it's probably safe to assume that it's going to diverge.
Is there an easier way to do this besides just like adding it up like that? No, that's just how you do it.
Yeah. Like on certain graphing calculators, you can do the command for the nth partial sum. So it'll nth partial sum of 4, it'll spit out 1.427. But if you're doing the homework and it gets tedious, then maybe once you've got the hang of it and you think you understand it, then maybe you can look at like online calculators to compute those things for you, because it does get tedious. Yeah, Nazim.
So is this like the basic procedure that we use for all infinite series?
Not all of them, no. We'll see there's different characteristics that we look at. But right now we're just kind of looking at the notion of the definition of an infinite series, comparing that to its nth partial sum, and then seeing, well, if we looked at the limit of nth partial sums, then that limit would go to infinity. So that's kind of what we're looking at here. Although we didn't go out that far, what we're saying is the limit, at least numerically, the limit as n approaches infinity on our nth partial sum is infinite, which means the series itself is infinite. I don't want to do that. Okay, so we're just kind of building up off the definition. We have infinity to the k plus 7 to the k. So we didn't come up with an explicit formula for the nth partial sum. We just looked at those things explicitly. So something like this example, if we looked at those as like fractions, it's a perfect example of why, in a lot of instances, looking for an explicit formula for the nth partial sum, it just doesn't make sense to do that. Because I mean, we could try all different kind of combinations. It's not as straightforward as 2 to the n minus 1 over 2 to the n, right? We might as well just look at the numbers. Do y'all have any questions about that?
Can you just factor the k out? Let's see. Like,
Are you looking at this one, you mean?
yeah.
To factor the k out? Are you thinking about the limit of that?
Yeah.
Everything's like
Okay. So here's the thing. We're not looking at a list of numbers anymore. If that weren't a sum, we could say the list, the numbers, right? Each term seems to approach what? Like if we looked at the very tail of just the list of numbers without adding them, what would they look like? They're approaching
2.
They're approaching 2. So way out here, like if we just looked at the series for this thing, way out here towards the tail, it's gonna be things like this. Way out there, right? But the sum indicates that we have to add all of those together to get the sum of that. So think about this. Think about it this way. We'll mention this because it does come up later. If I looked at this limit and I say, well, the tail just of each term is approaching 2, well, what does that mean? That means later out towards the tail, it's eventually you're adding 2 plus 2 plus 2 plus 2 plus 2 plus 2 forever, right? Which that, hopefully is very clear that diverges. So one of the necessary conditions for an infinite series to converge is that as we get closer and closer towards infinity, the tail of that, what would those terms have to approach? They would have to approach zero. Eventually, if we want an infinite series to converge, at the tail we have to be adding up 0 plus 0 plus 0, right? Because that way you're not accumulating any more number.
Is that a way to like quick check the sum? If you find that it doesn't equal 0, then you know that the limit as it approaches infinity diverges?
Yeah, we look at that as it's the divergence theorem, yeah. But depending on, there's room for misinterpretation of the divergence theorem. So let's just say, consider the limit as n goes to infinity, what we just said, of 2k over k plus 7 root k. That limit is equal to 2. But just please be mindful that just because you're computing a limit, that it in no way is telling you anything about the sum itself, right? Because all we're doing is computing the limit on each of the terms. We need to be clear that that's just going to give us the nth term. It has nothing to do with adding them. All right, so that's what we said earlier. If I think about it then in the context of, well, I've got to add all of those things together, what that's showing me is out towards the tail that the tail is approaching 2. So eventually you're always adding 2 ad infinitum with this particular series. So all that limit says is that the nth term, the tail of that sequence gets closer to 2. Does that make sense? Just because you compute a limit at infinity doesn't mean you're computing a sum. It just means you're computing a limit. It has nothing to do with the sum. That is, in context to the series, you're adding 2 plus 2 plus 2 at the end. Or towards the end. Say end. There's really no end, but
With just that evaluation there, is that enough? Without doing actually computing the S1 and the A1s?
yep.
You can say, well, I know it's going to end in 2, but I know it's a summation of that. So.
Right, so it will diverge, yeah. Yeah. I can't recall off the top of my head where the divergence theorem shows up, but it's good to keep that in mind because this is it's a primary test when you're given a series and it says, does this series converge? Like your first line of defense or your first test is the divergence test. If those terms at the tail don't go to 0, then there's no way that series can converge. Yeah.
If it goes to 0, does it always converge?
No. So just because the series approaches the tail, the terms approach 0, that is not a sufficient condition to say that it converges. It's a necessary condition, but it isn't sufficient. Okay, so we've got 1 over 3 to the k. The first 4 terms of the sequence of partial sums, and then make a conjecture about the value of the infinite series. We did look at 1 over 2 to the k, 1 over 3 to the k. There's one in your homework that's like 1 over 8 to the k. We'll talk about the pattern of the nth partial sum that these particular things, 1 over some number to the kth power, takes, because there is a formula for their nth partial sums.
So there is an easier way.
It depends on the series. This happens to be, this right here, and then 1 over 2 to the k happen to be a special type of series where we can find the sum. All right, so we first find the first 4 terms, and then we add those together. Okay, start with k equals 1, it's 1 over 3, 1 over 3 squared, 1 over 3 cubed, and 1 over 3 to the 4th. So S sub 1 is a third, S sub 2 is a third plus a ninth. Third partial sum, third plus a ninth plus a 27th. And then the 4th, third plus a ninth, 27 plus. That is 4 ninths, 13 27ths, and 40 over 81. Okay, so now we need to see if we can come up with a formula for the nth partial sum.
Equals 1.75.
These are our partial sums. Sequence of partial sums. So just like with 1 over 2 to the k, the denominators are really clear. This is our first partial sum, that's 3 to the first, that's 3 squared, that's 3 cubed, 3 to the 4th. Okay. So then we just need to reconcile the numerator in terms of the index 4, 3, 2, 1. How do we get when n is 4? How do we get 40 when n is 3? How do we get 13 when n is 2? How do we get 4? Okay, so just the easiest, you try to figure this out. I'm going to go ahead and just write down the generic pattern. Wow, that's a long page. This table. So we'll just have a few of these. We'll list our series, and then we'll list the, just for time's sake, we'll just list the nth partial sum. So far, the one we're looking at is from 1 to n of 1 over 3 to the k. So the formula for the nth partial sum is 3 to the n minus 1 all over 2 times 3 to the n. So in other words, the 3 to the n was the denominator, and the 3 to the n minus 1 over 2 is the numerator of that. So that's how we get the 40 and the 13 and the 9, or the 4 rather.
How do you see that?
Well, you could work it out for each
Okay.
one, or we'll just remember the formulas. Like for the one that's to the third, I can erase this, but it's basically because the partial sums are like this, right? So like that's the third partial sum. So basically what we're looking at with something like that, write it down, is like x to the n minus 1 plus x to the n minus 2 plus 1. Assuming that we were looking at 1 over 3 to the 0, for instance, that's x to the n minus 1 over x minus 1. So we have x, you could think about that as being factored as x to the n minus 1, expanding that times x minus 1. I don't know, I guess there's a few ways to look at that. But it's basically from here when n is 3, 3, 2, 1. So I don't know if that's helpful or not, but.
If you did have,
We'll
there's
just
not
write
one
these
right
out.
answer, right? You could do multiple different things, or is there always?
For the partial sum,
Yeah.
I guess there could be other representations of that.
Okay. Like for the numerator, I did 3n plus 1.
3n plus 1, like, but the denominator was still the same.
Yeah.
So I don't think that would work though. 3 to the n plus 1.
Just for.
So like if we would have 3 to the 4th plus 1 over 2 times 3 to the 4th.
No, 3 times n.
Oh, so this is not on top. It's not 3 to the n. It's 3 times n.
Yeah. And then just the same thing on the bottom. But I guess what I'm saying is you can have
Yeah.
different equations.
Mhm. Yeah, and so then if there's multiple ways to represent the nth partial sum, maybe one of those ways is more conducive to applying a limit at infinity. So you also want to keep that in mind. Because the whole point of finding the nth partial sum is so that we can take the limit at infinity. And if it's like, something weird where we have to do, I don't know, a whole lot of algebra or different, like L'Hopital's rule or something, I don't know. It might be a little more efficient this way. So like the nth partial sum for like the sum of 1 over 13 to the k would be 13 to the n minus 1 over 12 times 13 to the n. Maybe let's like 1 over 27 to the k. Nth partial sum 27 to the k minus 1 over 26 times 27 to the n. We're doing the nth partial sum. So I don't know. Maybe those three are enough to see the pattern with those types. They're good? Makes sense. So generic one, 1 over a to the k, nth partial sum is a to the k minus 1 over a minus 1 times a to the n. Sorry, I did it again. So that's the formula or the format that those things follow. And again, the a to the n minus 1 over a minus 1, that's the numerator of the denominator for these types of partial sums is always pretty easy to tell. It's just that number to the power. Okay. There's our nth partial sum for this sequence of partial sums. We listed formula. partial sum. So to make a conjecture about the series, we can look at the series, the infinite series is equivalent to the limit on the nth partial sum. So the sum from 1 to infinity of 1 over 3 to the k is the limit on our nth partial sum. So what does that limit equal to? 1/2, yeah, it's leading term over leading term. So we've got, this is equivalent to computing the limit as n goes to infinity on 3 to the n over 2 times 3 to the n, which is 1/2. So our conjecture is that it converges to 1/2. Do we know the sum of 1/3 plus a 9th plus a 27th plus a 181? 1 over 81 is 1/2. Do y'all have any questions on that?
This is because we found our SN, right?
Right. This, we know the sum of this series because we found the explicit formula for the nth partial sum and then took the limit. Yeah.
So this is saying that not the sum of everything converges to 1/2, but the nth partial sum converges to 1/2, right?
It's actually saying the sum converges to a half.
Oh, the sum.
The entire sum of this series converges to a half.
But we need to find that SN.
But you need to find the nth partial sum. Remember, because if we looked at just the limit of 1 over 3 to the k, as k goes to infinity, that's our original series. If we just looked at the limit of each term is approaching what? The limit of 1 over 3 to the k as k goes to infinity is 0. But looking at each term has nothing to do with the sum. So we said, here's something to do with the sum right here. That's when we looked at the limit of the sum. So this is the limit of the sum. The limit of the sum is the sum of the series. Yeah. But if you just look at the limit as this of the 1 over 3 to the k, that's just going to tell you what each term approaches as we continue on and on. So.
That makes sense.
Yeah. You're gonna save them, right? Your progress.
Just sitting in the closet.
How's the big one?
Good, we've gone on more walks.
Are we trying to bring down weight?
So I push back and I walk and he sits there.
Yeah, I didn't see that one. That's great. No, he's a lucky cat.
Okay, now she just gets carried around.
If I can do that to my dog. Super I just made a separation with some of my friends. I got to the very first problem. I was like, I have no idea. I know, I guess.
You
I
close.
would guess.
Oh my god, I literally, look at how many times I erased this page.
I couldn't do that. I literally couldn't.
Like,
I got to that.
literally took me forever.
I couldn't. That's the worst one I did because I was just like, I don't know. I punched in my calculator and I was like, maybe it's 0. See what happens. This one was the worst because I couldn't remember what the derivative or the and I did this. So I tried to work it out. That was
Yeah, this last one, I just like could not. It was just not happening.
Is that the one where it's really weird because of that stupid Ellen? We went over this, remember that? And I couldn't figure out if
Clearly, I
it was
did not
like.
remember it.
Well, I like remember the thing, and I was like, oh, it's like this or that, or just take the exam. All right, time to go exam for that test. Right now,
Oh my god, I did not miss that. I felt super nerdy at work the other day because I found this chemistry book about like what I'm doing, and I sat there reading it.
Hey, nice.
And the boss came in and was like, just
Get ready for a raise.
reading about gas chromatography. Like, is that not what everyone does? Come on, it's lunch break. Like feedback.
No, I meant I had it when actually. I got to the same point, plus Leo right there, and I got to the same point. I was in here, it's not serious.
Really?
Yeah, the professor said quite a bit better. It's just a lot more farther to actually just fly. I've never
You don't know that, right? Especially with Arrow.
I forgot the nine. One night I forgot the nine. Now it's the opposite. He had one night, I had nothing, I forgot the nine.
Yeah, I got this one. He goes, ow.